Okay, got it. Got it. And yes, we almost there. Okay, we are live. Okay, perfect, Gabby.
Yes. Click the. Okay. Yeah, as we discussed last time, the idea of this meeting to start remembering a lot of concepts that you already received during high school, probably. And the first part, oh, I can change this. Wait, there's the arrow. Yes, now it's, yeah. So basically, last time we discussed this map, right, with different, can you just, yes.
Gabby, I lost you.
Yeah, now it's okay. So we discussed this map with different aspects and fields or subfields in mathematics, and then we describe what we need to start doing that analysis and start implementing your models in your papers. And basically, those circles, it's hard to see actually. We're gonna start getting from those areas, especially the number system of the real numbers, the set theory, algebra, calculus, and probability, to start introducing statistical concepts. That will be the plan for these 15 episodes. And in this one, we are gonna start with the probability basics, with the probability principles only, okay, which is I would say is the easiest part to start. And then when we are moving forward from probability to statistical models, we're gonna start, calling some definitions and principles from the other areas. Okay, that will be the plan. So we discussed last time, like you could start using statistics in your own papers with different functional levels. You can start doing a completely fine statistical analysis with just the first level of understanding, the second level or the third level, depending on what is your purpose, right? Usually, if you go deep and deep, it's because you are refining and producing new models, new methods, right? But in the first level, it's enough to use previous functions, to use previous packages, let's say in R or Python, and also to understand the outputs, because the most important part is understanding the outputs and interpreting correctly what the software is telling you, right? So the first topic is about probability. So first, let's define probability in a very simple way. So probability is another way to say how likely something is to happen, right? And it's a field in mathematics to understand the uncertainty of events, right? So I think in general it's very intuitive, this definition, and we use this formula to define a probability, right? It's a probability. It's basically a ratio between the number of ways it can happen, an event can happen, divided by the total number of outcomes. That is the classic definition that I'm sure all of you know. And for instance, an example is, the chances of rolling a 4 with a die, right? So you just define the numerator and the denominator, and then you get the probability, right? The number of ways it can happen is just one, because only one side has a number 4, and you have 6 potential outcomes, right? That is very simple. Therefore, by definition, because you have a numerator that will be always, smaller or equal to the denominator, all the range of these values will be between 0 and 1. That's very, very important. That's important actually because sometimes when you are calculating in your models, you can get errors if you are calculating probabilities, let's say for some logistic regressions, and you're doing post hoc analysis. And then you can detect errors if it's not between this range. So it's very useful actually to remember that. And another property is like you could report this as a fraction, as a decimal, or as a percentage. So all of the three ways of notations are equally okay. And then another concept is that this is actually a guess of the reality, right? It's not a true. So we are only using probabilities as a guidance for different processes, especially for inferential processes, as we are going to discuss after. So another way to conceptualize this idea is to imagine that you repeat and repeat a lot of times this trial and then you get on average a number of outcomes. So for instance, let's say we want to see the probability of rolling four in a die, right? So we could do just the theoretical probability, which is 1 out of 6, or we could start throwing the die, 1,000, 1 million times, and then counting how many times 4 was present in your experiment, right? So that both are actually equivalent. You could do the thought process of imagine that you're repeating and repeating this for infinite times, and then you divide or you use a numerator of how many times the event appears, right? So therefore, we need to remember some important names, some important words that we're going to use across all these next episodes. The first one is the concept of experiment, right? Experiment is a repeatable procedure. So it's not an experiment like we believe or we know from basic science or chemistry or physics experiment. It's just a procedure. The point here, as in this example, let's say throwing a dice could be an experiment, needs to be repeatable, needs to be exactly in the same way reproduced a lot of times. So it's possible to be reproduced a lot of times. And the other property is like you have a specific set of possible results. So it needs to be a finite set of potential outcomes, right? Like in this case, from 1 to 6. Then another concept is the outcome. So the outcome is a possible result. And usually it's a, I don't know, in this case, a number or a description of the reality, and we call outcome, which is different than event. We're going to see that after. So then another concept is trial. So a trial is just one single performance of the experiment, right? The experiment is the concept, and a trial is how many you could repeat and repeat the experiment for a lot of trials. And then you have the sample space, which is another way to say all the possible outcomes, in this case from 1 to 6, right, in the throwing dice example. Then you have sample point, which is just one possible outcome, and it's kind of equivalent to your outcome in your trial, you see. And then finally, this is very important, is the event. So event is not the same that outcome. And this sometimes is confusing when we are doing logistic regressions or when we are doing any categorical analysis. So we need to know what is our outcome, and we define our outcome. Could be one or more outcomes, right? Sorry, we need to define our event, which could be one or more outcomes. And the outcome can be transformed. We could define a CADAF, we could combine two outcomes, whatever, and then we can call this as an event. For instance, in some trials, we could say that the main event is, be hospitalized or die, right? Mortality and hospitalization. So we use both as our event, but there are actually two outcomes. You see, that's why we are modeling in statistics events. We are not modeling necessarily outcomes. Sometimes an event is equal to outcome. That's a very, very important the differentiation, right?
Event's gonna be the one in a logistic, right?
Event it's usually the one or the two, right? Depending if you use the notation. But yeah, that's why it's very, very important for interpretation of odds ratios, relative risk, hazard ratios. We always need to know what is our event. And usually what we want in probability is to define the probability of the event, right? Of interest. Like we said here, let me go to the previous one. We said here, rolling a 4 with a die is actually our event, which in this case, it's only one outcome because it's just the number 4. Okay, that's clear. So then another important background information is that these events, which are the most important concept in probability, have different properties. So then we can say that there are special types of events. So for instance, we can call events that are independent, right? And probably you remember from PPCR, a lot of times we said, oh, the one of the assumptions of this test is independency, right? And then you just memorize that, and sometimes it's not clear why we said that, right? And it's independent because we are modeling events that are independent. And therefore, if you observe one event, that observation is not affecting the observation of a subsequent event. So they are completely, as the name says, independent in terms of the properties of the probabilities. Let's say an example here. So for instance, if we toss a coin 3 times and it comes up, as a head each time, right? What is the probability that the next toss will be a head, right? So in theory, it seems it should be higher, right? Or lower, sorry, because you already had 3 heads. So intuitively, you will say it will be lower, right? But it's not, because every time, if the coin is fair, every time you will have 50%, right? So both are completely independent. This is one important event. The other type of event is mutually exclusive, right? This one means like if one event happened, the other, because of the properties of your experiment, it can't happen, right? They are completely exclusive. So for instance, let's say we have the cards, right? And we wanna see the probability of having a eye and king, right? So you can't have both because they are the same, they are different types of symbols in the cards, right? But if you say a heart and king, then it's possible because you have one that could fulfill both categories. So that's a quick example of mutually exclusive and not mutually exclusive. This is very important to apply one rule, which is the addition rule for probability that you can see there, right? I'm assuming all of you are familiar with set theory, so I think this notation will be clear, but just as a reminder, we use the P, the capital P, to say probability, and between parentheses, the event. Then we use a notation of each event. So for instance, in this case, this one will be X, and the other one will be Y, and we use this kind of U-shape symbol to say that we are interested in the union of this, the joint probability. And then you just, in this case, because they are mutually exclusive, you just sum up the probabilities, okay? But if they are not mutually exclusive, right? If it's plausible to have both events happening at the same time, then this formula will be wrong. You will need to subtract the intersection, right? Like in this case, you will need to, because otherwise you're gonna count in that twice in your calculation. So you will need to subtract this to get the joint probability. Okay, this will be important next time. Just remember this and the set example, right? And any questions about this addition rule? I think it's very clear for everyone, right? Okay, so then another type of event, which is the dependent, right? This is actually very important because in all our clinical research, most of our events will be dependent, right? It's really hard, especially in clinical research, to have fully independent. We can say we assume they're independent. And if we are confident enough to assume that, we can do a lot of different statistical models. But most of the times we have some dependencies, which could be, full, completely dependency or partial dependency. So most of the times we have conditional events, and we're going to talk about conditional probabilities next time. But just remember, as example here, let's say drawing 2 cards from a deck, that's the example. And then when you are taking 1 card from the deck, right, already you have less cards, so your denominator is smaller. So you are changing the probability of the next card. You see, so that's why one event is directly affecting that, because it's or changing your sample space, right, or increasing that or decreasing that numerator. Could be in both ways. Remember, the sample space is the denominator, right?
Unless you put it back.
Unless you put it back. That's one way to assure independency, right? But in clinical research, it's hard to do that, right? Because you can't, change the exposure to the same patient and put the patient back to your sample, right? It will be impossible. But in theory, in these cases, it will be a way to maintain independency. So then this is just to clarify two very important things. Okay, so we have one that is called theoretical probability, which is the probability that we expect, and then the experimental probability, which is the probability that we calculate after we repeat the trials, right? This is so fundamental because what we are doing in research is to work with experimental probabilities, right? We calculate a sample from the population and we try to calculate probabilities from our sample. So we are always estimating the theoretical probability. So we work with estimates, right? But the theoretical ones, we call it parameters. So the theoretical probability is anything that you calculate from your population that you expect based on your assumptions. If we are frequentist, right? If we are Bayesian, we said based on our prior knowledge, right? But in this case, theoretical, it's always for the population and experimental is from our sample, which will be equal or almost equal if you have a really, really large sample. So that's why it's important to have a large sample and to be well powered so that you can infer correctly probabilities from your population, right? Using your sample. So that is a very important concept because the numerator, the denominator change. You see here in the theoretical, we say number of outcomes in the event and the total number of possible outcomes. In the experimental, you say the number of times of the event divided by the total number of trials. In our case, each patient is a trial because let's say we are using one treatment, right? We're using one treatment at a time in each patient, and then we calculate from one of them as a whole, right? So then everything that we calculate from the experimental probabilities, right, is going to be our classic table 1, right? Everything that we calculate from the population, like our confidence interval, our standard errors, all the things that are inferring information from the population will be actually a calculation of the theoretical probability, our estimation of the theoretical probability, okay? This is clear because this is very important. After, I think 2 or 3 more episodes, we're gonna start calculating things in different frameworks, okay? So it's clear? Great. So then let's now put this in context, right? Because so far we are talking about dice, coins, and that type of thing. So how we really use probabilities in clinical research. So we use it as statements in our papers, actually. And the numerator, most of the times, is how often an event or a characteristic occurs. Could be, how many of them die after the specific time, or how many of them have a reduction of pain of 20%. You could define any type of event or a combination of different outcomes, right? And the denominator would be the group of people that you use in your study. So most of the time, clinical research, the denominator is the number of your sample or your expected population. Okay, that's very important because that is our unit of analysis, right? And except if you're doing basic science, that could be the number of rats or a number of cell cultures, whatever, but it will be your unit of analysis. And as example, the probability of developing hypertension among smokers over age 65. Let's say this is one statement that we could use and try to calculate. Okay, now there is another special gap that I noticed when you are taking classes of biostatistics. You get this first module, and then you finish that, and then your next classes are about variables and normality distributions, but the connection is not always clear between this idea of events and outcomes with your study variables when you are operationalizing your variables in your paper. So this is the relationship. Basically, we define the outcome that at the end we are interested, and we kind of operationalize our event, and then we try to find a way to measure that event in our sample, and that measurement strategy becomes our study variable. Let's say an example, right? So for instance, here we are interested on pain changes. Let's say that, right? So then we need to define our event that could be, the pain changes clinically important, which is more than 2 points reduction, right? So we define that. The statement is, this is our event. We wanna know the probability of changing more than 2 points in our active group and the probability of changing more than 2 points in our sham group, let's say like that. But then you need to define a study variable to measure that event, which is our procedure, like could be using the bus, that we're using the BPI or the NRS, whatever, and then you use that to measure that event. You see, that is the sequence that you have in mind when you are doing that. Therefore, we are treating all our study variables as a random outcomes, right? So that means that could take any of several possible values. Therefore, we could use all the theory of random variables, random outcomes to calculate things about our study variables. You see, that is the important connection. And then in probability, we basically divide in two big groups. I know in PPCR and in all other courses of methodology, we want to be very, very clear of the types of outcomes and variables because we are designing the experiment, right? But in terms of calculating probabilities, we just care about these two big groups, continuous variables and discrete variables, or continuous events and discrete events. Therefore, the classic binary, the classic nominal, and are actually part of the discrete because we are counting how many times the option, let's say yes, of the binary outcome, it's happening. Let's say how many die, how many get a diagnosis, how many respond. You see, that's why at the end, in probabilities, we just have two big groups, okay? So then how we do this notation? Yeah, it seems is, yes, let me move this really quick. This one box. Okay, so then how we use this in the notations. This is important because we are gonna use it in the next sessions as well. We are use the P, could be PR or just P. We prefer to use PR, especially in epidemiology, because the P could be also used for prevalence, right? So that's why in epidemiology, they tend to use PR. So we're going to use PR because next times we're going to use examples from epidemiology because are easier to understand. But this is just the notation. We use the PR, then we use a bracket and the outcome, in this case, Y, and the level of the outcome, because we are talking about a binary outcome, 1 and 0, right? So then how you calculate this probability, you start measuring the person 1, person 2, person 3, and you start assigning one level. The person 1 was 1 because has that hypertension diagnosis. The 2 also 1, the 3 is 0, the 4 1, and so on. And then you count how many ones you got in your sample divided by your sample. You see, that will be 0.75, that could be 75% or 3 out of 4, right? So that is the way we are gonna use the notation in our next sessions, okay? I just wanna be sure the concepts are clear so far. And any question? I think it's just a quick refresh of all your high school mathematics, probably. Just connecting this with what we are doing, okay? And then finally, the last concept we're gonna discuss is the expected value. So the expected value is actually a measure of the theoretical mean. So we try to see, when you are doing an experiment, you try to find the probability that you believe will be the most likely, right? The expected. So then what you do is to repeat and repeat the experiment, the trials, a lot of trials of that same experiment, and then you try to calculate an average of all those possible outcomes. And then in the binary example, that's exactly what we just did. We can call this as the expected value of the number 1, right? The expected value of probability of having 1 in this sample is 0.75, as we just calculated, right? This is easy because you have 1 and 0. But if you have an expected value in a continuous variable, then you start having the problems here, because each person will start reporting a specific number, right? And then, for instance, you're going to calculate the average of those 4, and that will be your expected value. But what if you are not interested on that specific probability? that you, for instance, let's say you want to know the probability of having more than 120 milligrams of mercury, right? Millimeters of mercury. So then the exact count of the values in a continuous example is not enough, right? You need to create a distribution, and then you mark that 120 and calculate the probability, above that or below that. You see, that is why we need distributions to work with continuous variables. But with binary variables, we could actually just do arithmetic calculations, and we can create that's why you could do chi-square by hand, right? It's feasible because you count, you do expected and observe, and you get the final test statistic, right? But with continuous, you can't, because if you have distributions, you need to express a distribution as an integral to calculate the area under the curve, right? In that specific limit. And then you need to start solving those integrals, right? And nobody would like to do it by hand, right? Even though in some courses, actually in the school, I don't know if you're gonna take those courses, it's required to solve the integral of unit or binary models. But the idea of the integral is the most important part, not necessarily the calculation, okay? So that is the point, because what we need to use in our studies is these expected values. And these expected values will be defined by your null hypothesis, right? Usually 0. So then you start calculating probabilities against this expected value of 0 or no difference, right? So that's the general overview of the properties. Any questions so far? No? Okay, so next time, probably next Wednesday, will be after Christmas, right? Yeah, so next time we're gonna do the multiplication theorem and conditional probability. So now we are gonna start combining events, like what's the probability of having observing A given B, right? Given you observe other thing already. So then is when it start getting a bit complicated, but all the things we are doing, most of the things I would say are conditional. So that's why we need to really, really understand the properties and how we interpret conditional probabilities. Okay? Any question? No? Perfect. Yeah. So let me stop sharing to see if we have questions in our chat. Let's see. Professor, can you hear us? Can you see if we have questions in the, because we are streaming, right?
Yeah, recording. First professor.
I think it's in YouTube. Let me see.
Hey, Kevin. Hello, Kevin.
Yes.
Kevin.
Yeah,
Sorry, I was
you...
far from the button here, but I was listening everything.
Okay.
Let me just.
Can you see if we have any question there?
Chats in the chat, yeah, in the YouTube chat. Let me see here.
Almost said no.
We don't have anyone, Kevin. Is that for you and some too?
Okay, great.
Do not have it.
We don't.
We don't have it. Okay. So, Kevin,
Perfect.
and then wonderful presentation. I think this is a very good background, sort of a strong foundation, and this is essential for everyone. I can understand the basics, and the notation as well is important. And same as Kevin, I took it a lot of these courses in biostatistics and epidemiology, and again, you don't need to theoretically, but it is important, and all these courses, these notations, these basics and probability, how to define what is the event, what is the numerator, what is the denominator, and then understand the equation, the vocabulary. So that'll help you as well to move to the next steps. So very, very important. Kevin, that's wonderful. I think if no more questions, we can pass to Guilherme. I think everyone is digesting, and today was basics, but if no questions, then we can pass to Guilherme.
Yeah, because the idea would be to start you know, building a house, right? So this is really simple right now because it's the first part.